Hi, I'm Anchieri, a PhD student from the University of Bologna in the Department of Electrical, Electronic and Information Engineering. My research focuses on circularity and reliability optimization of power electronics inverters. In our group, we work on high-performance and reliable EV chargers, being an increasingly critical component due to the increasing adoption of electric vehicles. But now, let's go to the lab.
This is our modular experimental setup that we can use to test new topologies and control techniques for onboard chargers. At first, we check the correct operation through simulations. Then we use the same code to drive the experimental setup through the RTBox and evaluate the efficiency of the proposed systems using a power analyzer. In Europe, standards enable both single and three-phase residential charging, supporting up to 11 kW in three-phase mode and 3.6 up to 7.2 kW in single-phase mode. In this context, a typical onboard charger uses a two-stage architecture, a front-end three-phase AC-DC converter followed by an isolated DC-DC stage, a dual active bridge in this work. In single-phase operation, only two converter legs are active, naturally generating a second harmonic power ripple at twice the grid frequency. This pulsating power is handled by the input DC-link capacitor of the DC-DC stage, leading to a large value of capacitance and a bulky DC-link. To address this issue, in the literature a sinusoidal charging strategy has been proposed, which aims to reduce the required DC-link capacitance by transferring part of the ripple power to the switches of the DC-DC stage. However, transferring the low-frequency ripple to the back-end stage introduces additional electrical and thermal stress on the semiconductor devices, potentially impacting their runtime. That's why in this paper we provided a lifetime assessment of a single-phase onboard charger operated with constant and sinusoidal charging currents. A ripple factor K is used to control how the double frequency power component is shared between the DC-link capacitor and the MOSFETs, directly affecting their thermal stress and lifetime. As a result of this analysis, an intermediate value of K for both 3.6 and 7.2 kW achieves the optimal balance, maximizing overall system reliability. Finally, I would like to thank the authors of this work and the IEEE Industrial Electronics Society for the SIP opportunity.